Hello everyone! Maimbag amalem, maupay na kulo. This is Roy Siandan and I'm going to discuss connect section. For our objectives, at the end of 60-minute period, at least 75% of students should be able to A. Discuss how the eccentricity of a connect section describes its behavior. Letter B. Discuss the properties of different types of connect sections. And letter C. Describes the parts of the connect section and how connect section can be thought of across sections of double cone. Before I'm going to discuss our new topic this morning, let's have a motivation. This motivation code tells us, for the instruction, arrange the scrambled letter to make a word. Number 1. Correct! Hyperbola. Number 2. You got it right. Ellipse. How about number 3? Correct! Parabola. How about number 4? You got it right. Connect section. How about number 5? Correct! Eccentricity. How about number 6? Correct! Directrix. How about number 7? You got it right. Tangent lines. What is connect section? Connect section, or simply conic, is a curve obtained at the intersection of the surface of a cone with a plane. The 3 types of conic sections are the hyperbola, the parabola, and the ellipse. The circle is a type of ellipse, and it is sometimes considered to be 4th type of conic section. Conic sections can be generated by intersecting a plane with a cone. A cone has 2 identically shaped parts called naps. One nap is what most people mean by the cone and has the shape of a party hat. Conic sections are generated by the intersection of the plane with the cone. If the plane is parallel to the axis of the revolution, the y-axis, then the connect section is hyperbola. If the plane is parallel to the generating line, the connect section is parabola. If the plane is perpendicular to the axis of revolution, the connect section is a circle. If the plane intersects one nap at an angle to the axis other than 90 degrees, then the connect section is an ellipse. While each type of connect section looks very different, they have some features in common. For example, each type has at least one focus and directrix. Focus means it's a point about which the connect section is constructed. In other words, it is a point about which rays reflected from the curve converge. A parabola has one focus about which the shape is constructed. An ellipse and a hyperbola have 2. Directrix means is a line used to construct and define a connect section. The distance of directrix from a point in the connect section has a constant ratio to the distance from the point to the focus. As with the focus, a parabola has one directrix, while ellipses and hyperbolas have 2. These properties that the connect sections share are often presented as the following definition, which will be developed further in the following section. A conic section is the locus of points P whose distance to the focus is a constant multiple of the distance from P to the directrix of the conic. These distances are displayed as orange lines for each conic section in the following diagram. Parts of the conic sections, the 3 conic sections will be foci and directrices labeled. A parabola is the set of all points whose distance from a fixed point, called the focus, is equal to the distance from a fixed line, called the directrix. The point halfway between the focus and the directrix is called the vertex of the parabola. In the next figure, 4 parabolas are graphed as they appear on the coordinate plane. They may open up, down, to the left, or to the right. An ellipse is the set of all points for which the sum of the distances from 2 fixed points, the foci, is a constant. In the case of all ellipses, there are 2 foci and 2 directrices. In the next figure, a typical ellipse is graphed as it appears on the coordinate plane. A hyperbola is the set of all points where the difference between their distances from 2 fixed points, the foci, is constant. In the case of hyperbola, there are 2 foci and 2 directrices. Hyperbola also have asymptotes. Hyperbola, the difference of the distances from any point on the ellipse to the foci is constant. The transverse axis is also called major axis, and the conjugate axis is also called the minor axis. Applications of conic sections. Conic sections are used in many fields of study, particularly to describe shapes. For instance, they are used in astronomy to describe the shapes of the orbits of objects in space. 2 massive objects in space that interact according to Newton's law of universal gravitation can move in orbits that are in the shape of conic sections. They could follow ellipses, parabolas, or hyperbolas, depending on their properties. This is the real-life example of conic section. Galingan og mais diri sa barangay Don Enrique Lopez. Eccentricity, denoted E, is a parameter associated with every conic section. It can be thought of as a measure of how much the conic section deviates from being circular. The eccentricity of conic section is defined to be distance from any point on the conic section to its focus, divided by the perpendicular distance from the point to the nearest directrix. The value of E is constant for any conic section. This property can be used as general definition for conic sections. The value of E can be used to determine the type of conic section, as well as if E equal to 1, the conic is parabola. If E less than 1, it is an ellipse. If E greater than 1, it is a hyperbola. The eccentricity of a circle is 0. Note that 2 conic sections are similar, identically shaped, if and only if they have the same eccentricity. Recall that hyperbolas and non-circular ellipses have 2 foci and 2 associated directrices, while parabolas have 1 focus and 1 directrix. In the next figure, each type of a conic section is graphed with a focus and directrix. The orange lines denote the distance between the focus and points on the conic section, as well as the distance between the same points and the directrix. These are the distances used to find eccentricity. Eccentricity is the ratio between the distance from any point on the conic section to its focus and the perpendicular distance from that point to nearest directrix. Conceptualizing eccentricity from the definition of a parabola, the distance from any point on the parabola to the focus is equal equal to the distance from that same point to the directrix. Therefore, by definition, the eccentricity of a parabola must be 1. For an ellipse, the eccentricity is less than 1. This means that in the ratio that defines eccentricity, the numerator is less than the denominator. In other words, the distance between a point on a conic section and its focus is less than the distance between that point and the nearest directrix. Conversely, the eccentricity of a hyperbola is greater than 1. This indicates that the distance between a point on a conic section, the nearest directrix, is less than the distance between that point and the focus. Types of conic sections are particular type of shape formed by the intersection of a plane and right circular cone, depending on the angle between the plane and the cone. 4 different intersection shapes can be formed. Each shape also has degenerate form. There is a property of all conic sections called eccentricity, which takes the form of a numerical parameter e. The 4 conic section shapes each have different values of e. Types of conic sections. This figure shows how the conic sections in the light blue are the result of a plane intersecting a cone. Image 1 shows a parabola. Image 2 shows a circle bottom and an ellipse top, while an image 3 shows a hyperbola. A parabola is formed when the plane is parallel to the surface of the cone, resulting in a U-shaped curve that lies on the plane. Every parabola has certain features. First, a vertex, which is the point at which the curve turns around. Second, a focus, which is a point not on the curve about which the curve bends. Last, an axis of symmetry, which is a line connecting the vertex and the focus, which divides the parabola into 2 equal halves. All parabolas possess an eccentricity value e is equal to 1 as a direct result of having the same eccentricity. All parabolas are similar, meaning that any parabola can be transformed into any other with a change of position and scaling. The degenerate case of a parabola is when the plane just barely touches the outside surface of the cone, meaning that it is tangent to the cone. This creates a straight line's intersection out of the cone's diagonal. Non-degenerate parabolas can be represented with quadratic functions such as f of x is equal to x squared. A circle is a form when the plane is parallel to the base of the cone. Its intersection with the cone is therefore a set of points equidistant from a common point, the central axis of the cone, which meets the definition of a circle. All circles have certain features. First, a center point. Second, a radius, which is the distance from any point on the circle to the center point. All circles have an eccentricity. E is equal to 0. Thus, like the parabola, all circles are similar and can be transformed into one another on a coordinate plane. The general form of the equation of the circle is quantity x minus h squared plus quantity y minus k squared is equal to r squared, where quantity hk are the coordinates of the center of the circle and r is the radius. The degenerate form of the circle occurs when the plane only intersects the very tip of the cone. This is a single point intersection, or equivalently a circle of 0 radius. Connect sections graph by eccentricity. This graph shows an ellipse in red with an example eccentricity value of 0.5. A parabola in green with the required eccentricity of 1, and a hyperbola in blue with an example eccentricity of 2. It also shows one of the degenerate hyperbola cases. The straight black line corresponding to infinite eccentricity, the circle is on the inside of the parabola, which is on the inside of one side of the hyperbola, which has the horizontal line below it. In this way, increasing eccentricity can be identified with a kind of unfolding or opening up of the conic section. When the plane's angle relative to the cone is between the outside surface of the cone and the base of the cone, the resulting intersection is an ellipse. The definition of an ellipse includes being parallel to the base of the cone as well as, so all circles are a special case of the ellipse. Ellipses have these features. First, a major axis, which is the longest width across the ellipse. Second is a minor axis, which is the shortest width across the ellipse. Third, a center, which is the intersection of the two axes. And last, two focal points. For any point on the ellipse, the sum of the distances to both focal points is constant. Ellipses can have a range of eccentricity values. E is greater than or equal to 0 but less than 1. Notice that the value of 0 is included, a circle, but the value 1 is not included. That would be a parabola. Since there is a range of eccentricity values, not all ellipses are similar. The general form of the equation of an ellipse with major axis parallel to the x-axis is quantity x minus h squared over a squared plus quantity y minus a squared over b squared is equal to 1, where quantity h, k are the coordinates of the center. 2a is the length of the major axis and 2b is the length of the minor axis. If the ellipse has a vertical major axis, the a and b labels will switch places. The degenerate form of an ellipse is a point or circle of 0 radius, just as it was for the circle. A hyperbola is formed when the plane is parallel to the cone's central axis, meaning it intersects both parts of the double cone. Hyperbola have two branches, as well as these features. First is asymptote lines. Asymptote lines, these are two linear graphs that the curve of the hyperbola approaches but never touches. A center, which is the intersection of the asymptotes. Two focal points, around which each of the two branches bend. Two vertices, one of each branch. The general equation for a hyperbola with vertices and a horizontal line is quantity x minus h squared over a squared minus quantity y minus k squared over b squared is equal to 1, where quantity h, k are the coordinates of the center. Unlike an ellipse, A is not necessarily the larger axis number. It is the axis length connecting the two vertices. The eccentricity of hyperbola is restricted to e greater than 1 and has no upper bound. If the eccentricity is allowed to go to the limit of positive infinity, the hyperbola becomes one of its degenerate cases, a straight line. The other degenerate case of hyperbola is to become its two straight line asymptotes. This happens when the plane intersects the apex of the double cone. Tangent lines, no line can intersect a smooth conic section. more than 2 points. To prove this, substitute the equation of the line quantity x equal to a or y equal to mx plus b into the equation of the connect section and solve for x. The result is a quadratic equation. Ax squared plus bx plus c is equal to 0. For the x coordinates of the intersection, such equation have at most 2 solutions. As what have you observed in the figure of 3.14, lines intersecting as most conic. Lines that intersect the conic with exactly 2 points are secant lines. A line that intersects the conic in only 1 point is either A. Tangent to the conic, or B. A line that is parallel to one of its asymptotes if the conic is a hyperbola, or C. A line that is parallel to its axis if the conic is a parabola. Proposition 3.4.1. Let C be a smooth conic P, a point on C and F a focus. If C is a parabola, let D be the directrix. Otherwise, let F tilde be the other focus. If C is an ellipse, then the line that bisects the angle between the vectors negative P, F and vectors P, F tilde is tangent to C at P in figure 3.15. B. If C is a hyperbola, then the line that bisects the angle between vector PF and vector P F tilde is tangent to C at P, figure 3.16. And C. If C is a parabola, let R and element P be the point such that line segment PR is perpendicular to P. Then, the line that bisects the angle between vector PF and vector PR is tangent to C at P, figure 3.7. Thank you so much for watching this video, and God bless. Have a great day, everyone. Bye!